In the last 3 videos, we've been looking at the graphs of trigonometric functions. The graphs of sin x, cos x and tan x are traced out by what's called the unit circle. In this video, we're going to look at the unit circle and use it to find exact trig values for a range of special angles. So let's go ahead and look at the unit circle. This is the unit circle. So we have a circle and the length of the radius is 1 unit. We start at 0. We have the first quadrant just here, and this gives us now the acute angles between 0 and 90. As we move around anti-clockwise, we come to the second quadrant. The second quadrant are the obtuse angles from 90 to 180. In the third quadrant, we have now reflex angles. We've got 180 to 270, and then we move around to the fourth quadrant. So, in general, we move anti-clockwise through the 4 quadrants back now to 360 degrees or 2 pi radians. What we're going to do is look at how the unit circle traces out the graph of y is equal to sin x or sin theta. So if we start off now, we know that the sine of 0 is going to be 0. So this graph is going to be traced out. We know that the sine of 90 or pi by 2 gives us 1. The sine of 180 gives us 0. The sine of 270 gives us -1, and the sine of 360 gives us 0. And this cycles now infinitely to the left and to the right. So let's look at this then. So as we can see now, this hypotenuse of a right angle triangle is always going to be 1 unit. We've come up to a maximum, we're back now down to 0. Remember, we're defining the sine to be the opposite over the hypotenuse. So what we have now is the trace out, and this is how the unit circle works. So we can see now that the opposite is growing in length over there, and at that stage it's 1 over 1. We can see the opposite is decreasing to 0, that's why we get 0. We can see now that it's increasing to 1, but it's negative. And then we can see that it's decreasing. This is the opposite, the orange one is the opposite. And this is graphing now y is equal to sin x or sin theta. And as stated, that will keep going. We can do that for tan, we can do it for cos as well. Okay, so let's have a look at this. When we use the unit circle, sometimes we refer to it as the cast diagram. Shortly we're going to see why that's the case. So unit circle and cast diagram are often interchanged. So let's look now at our unit circle. So a quick sketch here. What we're going to have then is a circle, and it's going to have a radius of length 1. So if I just put this on, it's going to look something like so. So let's just put this in place. In fact, we'll make it just a touch bigger as we're going to start putting on some values. So let's put that there, and we'll just extend this. So if you were to plot this now, you would have this point here, which would be 1, 0, 0, 1. We would have now -1, 0, and then 0, -1. What we're going to do is introduce special triangles, and I'm going to write them here. We start using the special triangles to find exact trig values. So special, let's write this in, special triangles. We're going to have 2 of them. We're going to have what's called a 45, 45, 90 and a 30, 60, 90. So let's write it here, special triangles. So let's start off. Now the first one, the 45, 45, 90, is simply half of a unit square. So what we're going to have then is a square, side length 1, and then we're going to have that. Now if I cut this off with the diagonal, what we end up having now are 2 45-degree angles and the right angle. So here's the right angle. Remember, this is a unit, so 1, 1. We have a 45-degree angle, and we have now a 45-degree angle. So let's go ahead now and just think about this. If we wanted to find now the opposite, we could do that. We've got the adjacent, and the hypotenuse can be found simply by using Pythagoras. So we've got 1 and 1. 1 squared plus 1 squared is going to give us 2. Therefore, the hypotenuse is √2. So now we have all of the lengths of that triangle. And we call this now a 45, 45, 90. So we've got 3 now angles to a 45, 1 is 90. The next one that I'm going to do is half an equilateral triangle. So with this one, I'm going to put it to scale. We don't really need to, but it'll give us some idea of what we've got. This is called a 30, 60, 90 triangle. So if we put this on, 30, 60, and then we've got 90. I'll just move this down so I can place now the label on here. So what we have then is an equilateral triangle of side length 2. So this is 2. So all I've done is cut this in half. This angle is going to be 60 degrees. We know that the angles in an equilateral triangle are all going to be 60. Therefore, this is going to leave me 30. 60, 90, 30. This one is going to be 1. If we consider now, I've just cut the triangle in half. So we want this length here. Now this length is going to be the square root of 2 squared minus 1 squared, which gives me root 3. From this, we're going to build up a range of what we call special angles. So in a table, I'm going to put those special angles, and we will call the angle now x, or if we like, theta. So what we're going to have then is angle. I'll put it in radians, and I'll put it in degrees. We're going to have the sine of the angle, we're going to have the cosine of the angle, and we're going to have the tangent, or tan, of the angle. And all we're doing here is building up now a little table. In terms of you memorising or using exact trig values, and when we're talking about exact, an example of an exact trig value would be the sine of 60 degrees. The sine of 60 degrees is root 3 over 2, so that's an exact value. It's not decimalised, it's not written in terms of any, it's just essentially an exact value rather than some long decimal. So what we're going to have then is our values of x. So what we'll have x, and we'll put x here. So I'll do 1 in radians, 1 in degrees. We'll have now sine x, we will have cos x, and we'll have tan x, or if you like, theta. All it is now is an independent variable that we're choosing. So what we'll do, we'll start with 0. So this is degrees, this is radians. Now, we're going to start off by using these angles out of here, and then I'll complete the table. So what can we do? Well, we can do 30, so we can put 30 in. So 30 degrees. As now a radian measure, that is pi by 6, and we've seen that before. If we now look at the next one we can make is a 45 degree angle. 45 degrees is pi by 4. The next one we could make out of these triangles is going to be a 60 degree angle. 60 degrees is pi by 3. And then finally we're going to have now 90 degrees, and that is going to be pi by 2. These now are the acute angles that we can find exact values for quite quickly. So let's just go ahead. Let's start here. So let's do the sine of 30 degrees. Well, we'll go to this triangle. The sine is the opposite over the hypotenuse. So relative to the 30 degrees, this is the opposite, this is the hypotenuse. So the sine of the angle is the opposite over the hypotenuse. Therefore, sine of 30 degrees is going to be 1/2. 1 over 2. The cosine, well, that's the adjacent over the hypotenuse, so that is root 3 over 2. The tan of the angle is the opposite over the adjacent, so we can write this as 1 over root 3, or if you put this in a calculator, it will rationalise it to give root 3 over 3. Let's now look at 45 degrees. The sine of the angle is the opposite over the hypotenuse. Opposite over hypotenuse, sine of 45 degrees is 1 over root 2, or if your calculator rationalises it for you, root 2 over 2. Cosine adjacent over hypotenuse, same value, 1 over root 2 or root 2 over 2. If we now look at the tan of 45 degrees, which is pi by 4, it's the opposite over the adjacent, 1 over 1, which is 1. So we can see that we're building up these exact values. So if I said the tan of 45 degrees, or tan of pi by 4, the answer is 1. At this stage, hopefully we can see that now tan x is sine x over cos x. And we'll look at that as an identity as we go, but that's an important identity that you'll learn. Okay, sine x, well, sine of pi by 3, or 60 degrees, we need this particular triangle. So we've got now the opposite over the hypotenuse, root 3 over 2. If we look now at the cosine, the adjacent over the hypotenuse, 1 over 2. If we look at the tan, that's going to be the opposite over the adjacent, root 3 over 1, or just root 3. Okay, we know now that the sine of x is the cosine of 90 minus x and vice versa, and hopefully you can see that now with these values. If we just go ahead and finish this off, we need to fill out the 0 column. We know that the sine of 0 is going to give us 0, the cosine of 0 is going to give us 1, and the tan of 0 is going to give us 0. If we go to 90 degrees, we've got now the sine of 90 is 1, the cosine is 0, and tan is undefined. So we put now that it's going to tend to positive infinity, undefined. When we're trying to divide by 0, it's undefined. So if we look at sine, 0, 1/2, 1 over root 2, root 3 over 2, 1. If we look at cosine, it's now the opposite. 1, root 3 over 2, 1 over root 2, 1/2, 0. And then tan is simply sine over cosine. So what we've done here is built up some exact values for known angles between 0 and 90 degrees, or 0 and pi by 2. So how can we use this now in this particular case? Well, let's look at the unit circle. What we're going to do is build this up. I'm going to have now a 30-degree angle. So here is 0, here is 45. 30 degrees is just here. If I went ahead and pitched up a little right angle triangle, one of these, and just dropped it down, we can see the following information. So we know now that we have the unit circle. So this is going to be a 30-degree angle. So what we can say at this point right here now is that the sine of 30 degrees, so let's put this here, sine is going to be, and we'll put as 30, is going to be equal to 1/2. We can see that cos of 30 is going to be equal to root 3 over 2, and tan of 30 is going to be equal now to 1 over root 3, or root 3 over 3. So all we're doing is building up these special values for our known angles, and we're simply now working round. So if I wanted to put up a 45-degree angle, we could go ahead now and pitch up a 45, 45, 90. All I've done here is a 30, 60, 90, and this is our 60 and this is our 90. So if I put another one on, this is going to be a 45, 45, 90. So dropping this down, we can just go ahead and find these values. So we know that this is going to be 1, this is going to be 1, this is going to be root 2, and we can put on here now that the sine, so sine of 45 degrees, well, we know what that's going to be. That will be 1 over root 2, as will cos of 45 degrees, and then we will have now tan of 45 degrees, or we could say now tan of pi by 4, so tan of 45 is going to be 1. So remember 1, 1, and then root 2. So we got 1 over 1, which is tan, 1 over root 2, which is sine, 1 over root 2, which is cosine. And we can build this up. So why is it called the cast diagram? Well, here's the deal. This is now our value here. And what we have is A. We've got A just here. We've got S just here. We've got T just here. And we've got C just here. This tells us now in which quadrant each function is positive or negative. What I'm going to do here now is go back to a sketch. We're going to have now a sketch of, let's go ahead and start with sine x. If we think about the graph of sine x, as we did in the last video, we can see that sine x is positive in the first quadrant. So they were the angles from 0 to 90. It was positive in the second quadrant from 90 to 180, and then it was negative in the third and the fourth quadrant. So these are our quadrants. Now these correspond to Q1, which is this one right here. So this is Q1. So angles from 0 to 90, or pi by 2, is Q1. Q2, angles from 90 to 180. Q3, we've got now angles from 180 to 270. And Q4, we've got angles from 270 to 360. So we can see now that the sine is positive here. Sine is positive here. All values are positive here. And that's where we get our A from. So if we put here now, sine x is positive, we can see that corresponds to the S. If I now draw two other graphs, and we'll just go ahead and do those, let's do them on a different set of axes. I'll just increase this. I appreciate this isn't brilliant. but we'll do this anyway. Let's go ahead and do 2 more graphs. We will do now tan, and then we'll have cosine first, and then we'll have tan. So let's do what we're going to do. We'll do cosine. So cosine, in the first quadrant we're positive, the second quadrant we're negative, the third quadrant we're negative, and then the fourth quadrant we're positive. Positive, dot, dot, dot down there, negative, negative, positive. So we can see that all values are positive in the first quadrant. We can see now that the cosine is negative here. So if we wanted to put that here, let's put this here. Cos x is now negative. And then in the third quadrant now, we've got cos x is negative. And I'll put these on as well because I haven't put sin x on. Sin x is negative. Cos x is negative. And then in the fourth quadrant, of course, sin x is going to be negative and cos x is going to be positive. Okay, if we look at tan, what we have with tan, we come up, so let's come round here. We have our asymptote here at pi by 2. We come round to pi, or 180. We come up, another asymptote at 270, and then we finally have now this point right here. First quadrant, positive. Second quadrant, negative. Third quadrant, positive. Fourth quadrant, negative. All values in the first quadrant now are positive. We've got now in the second quadrant, tan x will be negative. We can see that in the third quadrant, tan x will be positive. Hence why we've got the t, and then tan x will be negative in the fourth quadrant. So all values, only sine, only tan, and only cos are positive in each of these quadrants. So we could say now that all these values, all acute angles, are going to end up being positive. So let's think about this logically now. So if I draw another circle up, the question then comes, if we just put this here, let's do some obtuse angles. So what we're going to have then is let's say we want to find now the cosine of 120 degrees. So we're moving now into the second quadrant. 120 degrees is in the second quadrant, and I want the cosine. So how are we going to do that? Well, let's think about this. If I drew a line just here, what we're going to have is this scenario. I want to now measure this angle right here. When we look at this, this doesn't give us an obvious triangle to pitch up. So this is going to be 120 degrees, and I want the cosine. What we can do though is use one of our triangles. If I drop a perpendicular down here, we will consider now this to be a 60-degree angle, as we've got now the straight line. So this is 60 degrees. So if this is 60 degrees, what we have here is now 2, we've got 1, and we've got root 3. If we think logically about this and look at the graphs, we can see now that the numeric value of an acute angle will be the same as the numeric value of 180 minus that. So if we look now at, let's say we've got sine of 30 degrees, that is going to be the same as sine of 150 degrees. So if I just run a line across here, 30 and 150, they give the same value. Now if I pick this point right here, let's say we have 60 degrees on the cosine curve and we have 120, the numeric value by symmetry is the same, but it just has a different sign. So what we could say is now cos of 60 will be equal to now the modulus of cos of 120. And when we're talking about the modulus, we're talking about the absolute value. So just the numeric value. And we can see that holds true with all of them. So for example now, if we had the tan of 45 degrees, that's equal to the modulus of the tan of 180 minus 45, which gives us 135. That means that we can still use these triangles now in the unit circle to find the value. The only thing we've got to consider now is the sign. So when I'm talking about the sign, I'm talking about whether it's negative or positive. So if we look now, we want the cosine, so let's write this here. We've got cos of 120 degrees. So if I want 120, I'm just going to use my 60, 30, 60, 90. So this is my 30. So let's think about this now. So I want the cosine. Well, that's the adjacent over the hypotenuse, and that's going to give us 1 over 2. Because we're in the second quadrant, only sine is positive, it's negative. If I wanted now the sine of 120 degrees, let's consider that. That is going to be the opposite over the hypotenuse, root 3 over 2. And we've got now a positive value as we've got now the second quadrant, and this is s. Only sine is positive. We can see that now in our graph. If we wanted the tan of 120 degrees, let's go ahead and write that out. So the tan of 120 degrees, well, the tan now is going to give us the opposite over the adjacent. That will give us now root 3 over 1. It's in the second quadrant, it's going to be negative. So only sine is positive here, only tan is positive here, only cos is positive here, and all are positive here. Hence cast, C-A-S-T. So that gives us a nice idea. Right, let's look at something slightly different. I've taken all of these to be positive values. We can work around the unit circle now in a negative direction. So let's say I wanted to pitch up an angle just here. And what I'm going to do is put now a 30-degree angle. So I'm going to say that this angle is going to be 30 degrees. If we consider now the little right angle triangle, all I'll do is drop that down. So what I'm going to have is the following. I know that this length is going to give me 2. I know that this length is going to give me now 1. And I know that this length is going to give me root 3. That is simply now the triangle that I've pitched up. It's not a very accurate diagram, but it just gives us now some idea. So there's our 60, we've got our 2, and all we've done is gone ahead and put those values on. What I'm going to do is find now the sine of minus 30. I'm going to find the cosine of minus 30, and I'm going to find the tan of minus 30. So this time we've gone round. We could of course say this is the same as the sine of 330 degrees, as this point here is 0 and 360. So if we go around the positive way, this would be 330. If we go negative, it's going to be minus 30. Well, let's look. We've got now the opposite over the hypotenuse for sine. That's going to be 1 over 2. It's in the fourth quadrant. Only cosine is positive here, so it's going to be negative. The cosine is going to be the adjacent over the hypotenuse, root 3 over 2. It's in the fourth quadrant, cosine is positive. We can see that from the graph here. The tan of minus 30 degrees is going to give us now 1 over root 3, and we need to ensure that we write that as a negative quantity as it's now in the fourth quadrant. So minus 1 over root 3, or root 3 over 3, negative quantity. That's if you rationalise it. So we can see now that we can find these multiples of 0, 30, 45, 60 and 90. And of course we can keep going with them. If we had something down here, we could go ahead and just write that out. So that just gives us some idea of how we can find these. If we look at these as well, we can see from the previous videos, we know that the sine is an odd function. So the sine of minus 30 is minus sine of 30. The cosine is an even function. So the cosine of minus 30 is the same as cosine of 30. And tan is also an odd function. Tan of minus 30 is the same as minus tan of 30. So this is an alternative way. If you wanted, you could just go ahead and memorize these. So we could keep going around the unit circle in a positive and negative direction to find our exact trig values. What we're now going to do is have a look at the unit circle fully labelled up. So this is a unit circle, nice old picture of it. So let's have a look at what we have here. Now if we look at these values, these are given now for sine and cosine, or cosine first and sine second. So if we look at this now, let's just go ahead. This is going to be now the 30 degrees, or pi by 6 radians. Over time you will need to know these in radians. So this is now the sine of the angle as we pitch up a 30-degree angle. So if I just put this on, let's go ahead and put our information. So let's do this. This is now a 30-degree angle here. We're going to have now the 60-degree angle here. we know that this is going to be 2, we know that's going to be 1, we know that's going to be root 3. All values are positive in the first quadrant, therefore now the sine of 30 degrees is 1 over 2, that's opposite over hypotenuse. Cosine is now the adjacent over the hypotenuse. So if we wanted to add tan, we would write down here now that this is going to be 1 over root 3. We can see as this increases, the length now of the hypotenuse stage 1, 45 pi by 4, that gives us a value. Let's just write now the tan. If we write now tan, we get root 3. If we write now tan, remember tan of 90 is undefined, as we can't have division by 0. Tan is going to give us the opposite over the adjacent. At this stage here, the length of the adjacent is 0. So now we're coming round. These are our obtuse angles, and all we did here, we saw 120 degrees, which is 2 pi by 3. If I wanted this one right here, all I would do, and I'll just quickly do this one, is pitch up now a 45, 45, 90. So if we have 45 here, 45 here, 1, 1, root 2. So we could say now that the tan of 135 degrees is going to be 1 over 1, and it will be negative, as we've only got sine to be positive in the second quadrant, Q2, Q1. And we go round. We've got now our value here. This is going to give us firstly our cosine, then we're going to get our sine. We got our cosine and we got our sine. And of course we could put these on for tan and so on and so forth. So we'd end up with 0, we would come round. Here we would have now positive 1. This is quite a nice one for tan, as tan, we haven't really looked at tan. Tan is positive in the third quadrant, as we've seen graphically, and now we can see from the unit circle. So 5 pi by 4, or 225 degrees, I'm going to pitch up now a little right angle triangle. This is going to be 45, 45, 90, 1, so we've got our 1 here, we've got 1 here, we've got now root 2. So opposite over the adjacent, 45 degrees, therefore tan of 225 degrees, or 5 pi by 4 is 1. And again, you can work with symmetry if you want to look at it like this. Another way to think about this is if we have now a solution here for a value of tan. We know that tan of 1 is here. Tan cycles every 180 degrees. If we look at this, and let's just move on a second. Let's look at how we can use this for symmetry. So if you wanted, and I'm not suggesting you have to do this, let's just get the unit circle back up, and we'll put some axes on. If we think about now the definitions of sine and cosines, let's write these in. So if we have now sine x, so if we have sine x, this is the same as sine of 180 minus x. It's also the sine of x is sine of 360 plus x, and we'll see how we can get solutions to that. Cos x is going to give us cos of 360 minus x, and then tan x gives us tan, so let's write this in, tan of 180 plus x. So if we think about sine, sine's nice and straightforward. So if we have 1 here, 30 degrees in, by symmetry we will have 1 now 30 degrees back from 180. If we have now the cosine, let's look at a cosine. If we have 1 60 degrees in, we will have 1 60 degrees back from 360. So if you know this angle, you know this one. If you want this one, you can work out this one. And then tan cycles every 180. So if we have 1 just here for tan, then we'll have 1 here. So essentially what this is now, let's just look at this. This is x, and this is going to be 180 minus x. And we'll have the same numeric value. This one is going to be, let's call this y. This is going to be now 180 plus y. So 180 plus y. This one, let's call this z. Not really a fan of using z right there, but this is going to be 360 minus z. So we can see how now by symmetry, so if we said cos of 60, well that's going to be now, we know that's 1/2, therefore cos of 300, we could simply use that value now to find this one. So with the unit circle, there's lots of scope for manoeuvre. So there we go. So you now have three choices in terms of the way you look at trig graphs. You can look at them purely in the traced out form. You can look at them at the unit, as a unit circle. You can combine the two. I often combine the two to get some idea. Also, you can simply learn that table of values and consider subsequent solutions based on these. So if we were solving now that sine x was equal to, for example, 1/2, then if we were interested in this between 0 and 720 degrees, I could do one loop. I'd pick this up as my first solution. I'd pick this up as my second solution. I would come round. I would pick up this one now as my next solution, which is 360 on. And then I'd pick this one up as my fourth solution, which is again 360 on from that. So when you come to solve equations, you can do that. So there we go. Brief introduction to the unit circle or the cast diagram.